Hello everyone, I hope you're doing well. On this channel, I share videos that highlight the importance of mathematical modeling techniques. Today, I will talk about the transiently rapidly increasing numbers discussed in Chapter 2 of the first paper on the Collatz Conjecture that I published on Zenodo. I also uploaded a follow-up paper on May 22nd, which provides a concise summary of this topic. I will explain the contents of that follow-up paper in a later video as well. In the Collatz conjecture, the values generated by the iterative calculation vary widely depending on the natural number chosen as the initial value. Some sequences increase only slightly before quickly reaching 1, while others undergo repeated rises and falls before finally arriving at 1. Among these sequences, there are some that exhibit particularly distinctive patterns of change. Let us take the initial value n0 equals 27. Since this number is odd, we multiply it by 3 and add 1, obtaining 82. Because 82 is even, dividing it by 2 gives 41. As we continue this calculation process, the calculated values exhibit a temporary surge starting from a certain point, as shown in the figure. After reaching the maximum value of 9,232, the sequence decreases and eventually reaches 1. The total number of iterations is 111. I refer to natural numbers that produce this kind of behavior as transiently rapidly increasing numbers, and I use them as examples in the subsequent discussion. Among the natural numbers up to 100, the transiently rapidly increasing numbers that exhibit behavior similar to that of n0 equals 27 are 31, 41, 47, 54, 55, 62, 63, 71, 73, 82, 83, 91, 94, 95, and 97. For each of these initial values, the calculated sequence merges into the sequence of n0 equals 27 immediately after performing either the calculation 3n0 plus 1 or the calculation n0/2, as shown in this table. When observing this kind of behavior in the calculated values, we might wonder whether there exist natural numbers whose calculated values continue to increase without bound. However, no such natural numbers exist. In a later video, I will prove this using a criterion that rules out this type of change, so we can be assured that such behavior does not occur. The number of iterations for initial values up to 100 is shown in this figure. We can see several points where the number of iterations becomes relatively large. These correspond to the transiently rapidly increasing numbers, whose number of iterations is around 110. For all other natural numbers, the calculated values reach 1 after roughly 30 calculations. This table summarizes, for initial values from 2 to 100, the number of iterations required for the calculated values to reach 1, the maximum value that appears along the way, and the number of iterations at which that maximum value occurs. The entries corresponding to the transiently rapidly increasing numbers are highlighted in yellow. From this table, we can see that most of the maximum values remain below 300. In any case, no two initial values exhibit exactly the same behavior. As n0 becomes larger, the number of iterations also increases, but the rate of increase is small. For reference, even when n0 equals 10 to the power of 100 plus 1, the number of iterations is at most 2,173. This suggests that no matter how large the initial value becomes, the calculated values tend to decrease relatively quickly and eventually reach 1. Let us look at an extreme example. For this very large initial value, the calculated value reaches its maximum at the first calculation and then decreases rapidly, reaching 1 after 247 calculations. However, during this decrease, the calculated values change in a highly intricate manner. The difficulty in proving the Collatz conjecture lies in the fact that we must show that the calculated values eventually reach 1 for every natural number. I encourage all of us to think about how this fact might be proven. That concludes today's talk. I look forward to seeing you again in the next video. Until then, take care.